Okay, so hi, good morning everyone. This is Vishal Ahuja. So today's webinar is about BMS hardware masterclass, right? So let us see what we'll be covering in today's session. In today's session, we'll be covering the fundamentals of battery management system hardware design, different monitoring circuits which are there in the part of as a part of BMS. We will also see what are different control and functional circuit of a BMS. Then we'll deep dive into BMS protection circuits like short circuit, over voltage, so on and so forth. At the end, we'll give a brief introduction about the Techlanz. So today's speaker, Mr. Amit Kumar is with me. He has around 13 plus year experience in the EV industry. Currently, he's leading the BMS hardware at VinFast in Vietnam. He has worked with Bosch, BEL, Mahindra, INL, and other companies also. A very rich experience in hardware design. So he will take us through in this journey and we'll discuss more about this. Amit, over to you. So you can present your screen and stop my video. You can turn on your video.
Okay, thanks, Vishal. Okay, let me share my screen. Okay, so hi, hello everyone. Myself, Amit Kumar, and today we will look into some of the basic concepts that are involved with battery management system hardware design. Okay, so going ahead, we all have this particular question in our mind that what is BMS and is it just a minute. Okay, so what it does and is it an electronic device? So like this, we have a couple of questions in our mind. And is it mandatory to have in our lithium ion battery pack or and how it is designed and many more questions like this. So we will go into this seminar or in this webinar and look into all of these questions. Okay, so in our day-to-day life, we come across many electronic gadgets such as mobile phones, laptops, and of course, electric cars. So we have lithium ion battery pack in all of these equipments. And because all of these equipments have lithium ion cells or batteries, we definitely have BMS in all of these devices. So these are a couple of examples that I can show it to you. And of course, there are many more like Bluetooth speakers and headphones, many others. Okay. And going ahead, as you can see on your screen, this is a generic block diagram of a battery management system. So over here, what all things we have? Okay, let's go into one by one. So we can see there is a battery. There is, of course, a fuse over here. Let me open my cursor. Okay, we have a fuse. We have a Hall effect sensor, and we have a contactor. This is the positive side contactor. We have a pre-charge resistor, and then there is a HV connector over here, and we have a pyro fuse, we have a shunt resistor, we have a negative side contactor, and in the middle, we have a BMS controller. So this particular BMS controller, what is the main job of this BMS controller is, so battery management system is a collection of all the electronics and electrical devices that controls the battery pack. And battery pack in a sense, like it is, of course, a rechargeable battery pack. And what is the prime function of a BMS is to manage this battery pack within its operatable conditions. So this is what the basic block diagram of BMS looks like. And we will discuss about all these electronics and electrical components in our later slides. Okay. So let's move ahead. And before moving ahead, let us discuss briefly what are the main functions of BMS and what all algorithms it used to handle. So as you all have already heard about that it used to monitor cell voltage, cell temperature, and it also used to have estimations such as state of charge, state of health, and state of energy. And it also used to control some of the basic functions like charging, discharging, cell balancing, and a couple of more functions it used to do. And it also used to protect our battery pack from overcurrent, over voltage, over temperature, under temperature type of events. And it communicates all the data that it collects from the battery pack to another ECUs. ECUs means electronic control unit that are available in the vehicle. Okay, so one of the prime function that a BMS should do is cell voltage and temperature measurement. So over here you can look that there is a BMS controller and there is a string of cells. We have like this, we can have multiple cells. Like over here, I have shown just an example. So we have cell number 1, cell number 2, cell number 3. Like this, we can have multiple cells till cell number n. And we also have temperature sensor that is connected to individual cells. So what is the main function of BMS when it comes to cell voltage and temperature measurement? That a BMS used to measure cell voltage from each and individual cells in the string of cells that makes up a battery pack. So we can see over here how a BMS controller is connected and how individual cell nodes are connected to the BMS. And each individual cell nodes, BMS used to collect the cell voltage information from each cell. So this is just a block diagram. Over here we can see an example of a small BMS that is controlling 4 cells in series. So over here you can see how this BMS, this is just an example of a small BMS. And these are the 4 cells, and we can see the cell negative and cell 1, cell 2, cell 3, cell 4. Individual cell points or the voltage or terminal, we used to say these are the cell terminals, are connected to this BMS. And like this, it used to measure the cell voltage. And of course, over here, I have not shown you that how the temperature points are captured, but we will discuss about this in detail in the next courses. So there will also be temperature sensors which are connected to each cell, and those temperature sensors will be interfaced to BMS. Another function that BMS does in the battery pack, over here, you can see that it used to measure current. And why current measurement is important? Because based on current measurement, BMS used to determine the capacity of the cell. Capacity, in a sense, when I say capacity, it means another abbreviation of capacity is state of charge. That how much charge is left in the battery, that is determined by Coulomb counting. And how BMS does Coulomb counting is by measuring the current flowing in and out of the cells. And this is one example of the current sensor that connects with the cells along with the loads. So, and some of the examples of the shunt you can see on the screen over here. So this is a normal copper shunt, and there is an element that is called magnanin. So what is this magnanin? Magnanin is a resistive element that is an alloy of copper, and the resistance of this element remains very stable over large temperature variations. And therefore, we use magnanin to determine the current flowing through the battery pack. And what is the equation that we use to determine the current? Current is nothing but the voltage developed across the shunt element. So there will be one shunt element like this, and BMS used to measure the voltage drop across these 2 points. That means on the left side and the right side, there will be terminals which goes inside the BMS, and BMS measures the voltage difference across this magnanin element. And that voltage difference is proportional to the current flowing through this element. And based on that, BMS used to determine how much current is flowing through this resistive element. Okay. Moving ahead, this is another example of current measurement, and how this is particularly called Hall effect sensor. So what is the principle that involved in measuring current using a Hall effect sensor is, we have a conductor, or this is called a copper bus bar, or any type of a bus bar that carries current in and out of the battery pack, and we have this sensor around this bus bar. And how does this measures? In our schools, or in our colleges, we have learned about right hand thumb rule. So if my current in this bus bar is flowing in this direction, it will generate a magnetic field that is proportional to the current flowing in this conductor. And that circulating magnetic field interacts with a silicon device that is kept inside the sensor. And then this silicon device generates a proportional voltage that is proportional to the magnetic field generated in the shunt in this Hall sensor, in the Hall effect sensor. And that voltage gets amplified, and BMS reads this voltage to determine how much current is flowing through this conductor. So, and some of the examples of Hall effect sensor we can see over here. So this is some of the Hall effect sensor we can see. So you can see there are 4 different types of Hall effect sensor, and there is, you can see that there is a slot built inside the Hall effect sensor. And why this slot is present is, through this slot there will be a copper bus bar that will pass, and inside this sensor there will be this amplifier circuit that will be inbuilt inside the sensor. And through this amplifier circuit, the BMS will read what is the voltage, voltage is coming out from the sensor, and that voltage will be proportional to the current flowing through the bus bar that is going through this Hall effect sensor. So this is one of the example of some of the examples of Hall effect sensor. Okay, so going ahead, there is another function that BMS does, is turning on and turning off the power to the loads. And how it does, one of the example is through the contactors. Contactors are nothing but, you can imagine these contactors as a general purpose relay. How a relay works: when you energize the coil, the main contact inside the relay connects, and the current starts flowing through the main contacts. So over here also you can see these are the 2 examples of the contactors. And it sometimes some people call this as contactor, and somewhere you will see that they call it as a relay. Both are interchangeable. It's how would I say, like it's just a means of easiness. Like someone calls it as a contactor, someone calls it as a relay. That doesn't matter. And what it does, when you energize it, it turns on the contacts inside, and you will and the current will start flowing through these contactors. And we have these contactors on the positive side, on the negative side, and we also have one pre-charge contactor and a pre-charge resistor. So we will see the detail about these in coming slides. And there is another way BMS can operate power on or power off of the battery pack, that is using MOSFETs. So over here you can see there is 2 MOSFETs connected back to back, and these 2 MOSFETs are operated to control the current flowing in and out of the battery pack. So when the current will flow in is during charging, and when the current will flow out, that is called discharging. So over here we can see there are 2 MOSFETs. One MOSFET over here is operated while during charging, and another MOSFET it is operated while during discharging. And we will see about these in detail in the main BMS course. And over here, you can see there is a PCB. And on this PCB, you can see some of the MOSFETs connected over here. These are the back-to-back MOSFET switch. And over here, we can see there are multiple switches, and not only on one switch on the charging side and one MOSFET on the discharging side, but we have multiple switches. Why these switches are coming in parallels? Because to share the load current. So depending upon how much current we want from our battery pack, we need to have multiple switches in parallel on the charge side and on the discharge side. This we will look into detail in our battery pack course. Okay. So another function that BMS does is of pre-charging. So I would say many of us used to think what is pre-charge. Probably many of us would also heard about this. The BMS does pre-charging. So we will look into this in a bit detail. So why pre-charge is required? Pre-charge is required to while turning on power to the HV load. Why? Because as you can see, there is a capacitor over here. This capacitor will be present in almost certainly all of the electronic loads. And these capacitors are called DC link capacitors or CX capacitors. So what happens during HV when we turn on the power to the loads? So you can see, imagine this is a capacitor, and this capacitor will be in discharge condition. And the moment we connect HV positive, HV negative contactor, there will be a sudden inrush current flowing through this capacitor, because we know how capacitors behave. When capacitor is discharged, it generally used to conduct a lot of current when you apply a voltage across the capacitor. It generally acts like a short circuit for a small period of time. To protect our contactors from getting welded during HV turning on time, we do something that is called pre-charge. Now let's see how pre-charge works. Before turning on my HV positive and HV negative contactor directly, we allow this capacitor to charge slowly, so that during my HV turn on current, we don't get a high inrush current. So what we do, we have made over here a pre-charge section. We can see that there is a pre-charge relay and a pre-charge resistor over here. And when we turn on, before turning on my HV positive contactor, and we turn on pre-charge contactor. So how my current flows during pre-charge is, we can see over here from the battery, the current goes out through this pre-charge contactor, through my resistor, and goes inside the load. And from the load, it goes out through negative contactor back to battery. Because of this resistive element and the capacitor that we are trying to pre-charge it before we turn on HV, we call this as pre-charge. So how this particular waveform will look like? We can see that when during pre-charge, the voltage increases like this. This is called the RC time constant. And due to this, we don't get a high inrush current flowing out of my battery pack. And because of this, we protect our HV positive, HV negative contactors. So you can see over here, I have drawn a small graph, the sequence how we operate these contactors during pre-charge. Okay, so let's analyze this graph. So how we do in the beginning? So we first turn on HV negative contactor. Okay, so you can see here a graph, HV negative contactor turns on, and at the same time, we turn on our pre-charge contactor. So first we turn on our HV negative contactor, then we turn on our pre-charge contactor. And because of this, the current starts flowing in this direction through this R and C. And then after certain time, we turn on our positive contactor. Okay. So due to this, we reduce our inrush current. So, and this example, let's look into this much more in detail. I will show you one simulation. Let me bring the simulation part over here. Okay. Okay, so over here we can see that.
So you have to share that.
Okay, just
only presentation is being shared right now.
Okay, just a minute, Vishal. I'll share my screen.
Yeah, if you want to take a water break also, Amit, you can. I think you can take a sip of water also.
I hope you can see my screen.
Yeah, visible.
Okay, good. Okay, so over here, let me explain you how precharge works. So as we see over here, we have a voltage source. This will simulate a battery. Okay, we have this switch as HV positive contactor, and we have another switch, this one, which will act like a precharge contactor. We have a 47 ohm resistor. We have one capacitor of 1 millifarad. This capacitor is nothing but the DC link capacitor that is present in the car or any automobile. And this is my HV negative contactor. Okay, so let us first see how this particular circuit behaves with precharge. Okay, so before going ahead, let me show you another thing. So I have simulated this switch as you can see over here how I have programmed the switch. These are the time controlled switches. Okay, so first over here, this switch will turn on at 0 second and it will turn off at 300 millisecond. The second switch, which is HV positive switch, this will turn on at 290 millisecond and turn off after 2 seconds. This 2 second is nothing. It is just like end when we want to end the simulation. And my negative contactor over here, it will turn on at 0 second and it will go up to 2 seconds. So let us first run this simulation and see how it behaves. Okay, what I have done over here, I have put two cursors. Okay, one is cursor A, cursor B. Cursor B is on current waveform and cursor A is on voltage, my voltage waveform. So as you can see, because I have turned on my precharge switch at precharge and my negative, first I'm turning on my precharge and my negative switch. So how the current will flow through this, through the capacitor, and then go back to my voltage source. And you can see how the voltage waveform is generated. The precharge function or the RC time constant, you can see how the capacitor is charging. And we have a voltage source over here, which is measuring this voltage. And we all can see how this particular voltage is charging and during this time, what is my maximum current that peaks up. This is, as you can see, it is approximately 6.1 amps. Okay, and because of this, I don't have a high impulse current flow or inrush current flowing through this capacitor during my pre-charge time. So let us reverse this situation. Okay. Let us see when we don't have this pre-charge, when we just simply have my HV positive, HV negative contactor, how my voltage waveforms will look like. Okay, so what I will do over here, I will just delete these two. Okay. I have deleted my pre-charge path. And what I will do, my time, this time controlled switch is I will turn on this HV positive also at 0th second, and my HV negative also is turning on at 0 second. That means my HV positive and HV negative both turns on at the same time. Let us analyze this one. Let me put a small time delay in my HV positive. Yeah. Let me zoom a little bit. Okay, so this time what I see when I turn on both the switch almost at the same time, my current peaks up to approximately 25 amps. Previously, it was only 6 amps. So this shows that we have a little bit more current flowing through my DC link capacitor when we turn on both the switch at the same time without having the pre-charge resistor. And why this particular function is important is, so okay, let us go back to our slides. Okay, so over here, so why this particular path, as I think we will get more into detail about this calculation of why this particular resistor and how this particular resistor is the value is calculated much in detail in our main course. But I hope most of us would have got this hint of why this particular path is required during HV turn on. This path, exactly why it is required, is to lower down my inrush current during HV turn on when we have a DC link capacitor connected.
Can you go full screen of it?
Okay. Okay. Yeah. Okay, so going ahead, we have another function that BMS does is discharge function. So what happens after pre-charge? Of course, as we have seen before, that first it will do pre-charge, and after pre-charge, it will turn on my HV positive, HV negative contactor. So now during discharge function, BMS has to monitor continuously my battery terminal voltage and battery temperature. And of course, there are many other things that BMS used to do during discharge. But over here, you can see during discharge, what happens? My battery the cell will be in discharge mode. And this is one example of my discharge characteristics of my lithium-ion battery. So over here, how my discharge characteristics of my lithium-ion battery looks like. During full charge, we will have around 4.2, 4.25 volts. And as my lithium-ion battery discharges, the voltage will come down, and then from almost around 80% to 20% of my SOC, or I would say the capacity of the battery, my voltage remains almost flat, and after 20%, it starts to come down. So during this time, what BMS does, BMS used to monitor my cell voltage, cell temperature, and it also used to measure the current and all other operational parameters and delivers the power to the load. So this is what the discharge function is in the battery pack in our battery pack. And so, okay, so first, what is the steps? So, okay, let us look in terms of steps. So first step, BMS does the pre-charge, okay. Second step, BMS turns on HV. Third step, BMS measures, that means during discharge function, BMS measures cell voltage, cell current, and cell temperature during its entire discharge mode, or during that time when my discharge is on. Okay, and the next function what BMS does is charging. So BMS also controls charging of my battery pack. So what happens during charging? So my load gets replaced by a charger, and the current, instead of flowing out of the battery, the charger pushes current into the battery and charges the battery. So first difference that we have during discharge mode and charge mode is the reversal of current direction. So current direction reverse during charging, and it charges the battery pack. And during charging also, BMS has to monitor how much charge or how much current is flowing inside the battery, what is the battery voltage, so that it can operate the battery within the safe operatable limit. So over here, let us look how the charge function looks like. So here is one graph, as you can see that during initial time, my BMS allows constant current going into the battery. And then after this constant current mode, it goes into constant voltage mode. So first stage, my BMS controller allows the battery pack to charge in constant current mode. And in second stage, it goes into constant voltage mode. And what is the parameter that BMS measures to go out from constant current to go into the constant voltage mode is my terminal voltage. Over here, as you can see, upon hitting a specific terminal voltage, this red color graph is my cell voltage. After hitting a specific cell voltage, my BMS switches over from constant current to constant voltage mode. And it allows constant voltage mode until certain time. As you can see, this green graph, what it represents the SOC. Blue graph represents the current. Red graph represents my cell terminal voltage. So based on my cell terminal voltage, BMS switches over from constant current to constant voltage mode, and then it continues in constant voltage mode until my SOC reaches 100%. And different BMS has different cell terminal, because as we know that different cell has different terminal voltages. And because of that, if we use this BMS controller like for LFP cells or for NMC cells or for LMFP cells, this particular switch over time from constant current to constant voltage will vary. And yeah, so as we know, like this will vary based on the chemistry of the cell, that we used in our battery pack. Okay, hope this will be understood from most of our panelists. And okay, and going ahead, we have one more function that BMS does is cell balancing.
Amit, I think we are facing some disconnectivity. Requesting all of you to hold for a minute while Amit joins back. Think he's facing some issues. 1 second. Okay, no worries. Meanwhile, I'll continue the session. Let me share my screen. When Amit join, then he will start from where he left it. Okay. Yeah. I hope my screen is visible. Right. So what Amit was explaining, the cell balancing part of it. Now, what happens in cell balancing that you have individual cells, right? As a complete battery pack, there are some uncertainties. So not every cell is manufactured the same way, right? So there are some manufacturing differences, some charging differences. What happens sometime a cell gets charged before the other cell gets charged, right? So while suppose you have 10 cells which are being charged by a charger in a battery bank, it's quite some time what happened that one cell gets charged prior to other cells. Now, since you are reading a voltage, right, and the things are connected in series, you see that this cell is already charged. You cannot overcharge it. There are some threats associated with that, right? So what you do is there is a cell balancing circuit. We have active cell balancing, we have passive cell balancing. In passive cell balancing, what we do, we start dissipating the energy via some resistor. So what happens if you see this in this circuit, we activate this circuit via controller. Let me use pointer. Okay, so what we do via controller, for suppose the cell 1 is charged, okay, and what we do is while the cell is being charged and we are monitoring its voltage, we start dissipating the energy of this cell via this resistor. This is how the balancing works. So meanwhile, the controller is charging, the charger is charging other cells, while this cell has achieved 4.2 voltage or whatever the threshold is there, you start dissipating the extra energy which is being coming to this cell via this resistor, right? This is how the cell balancing happens, the passive cell balancing. In active cell balancing, you don't dissipate the heat because at the end, whatever the energy is being consumed by the charger, right, which is sending back to the battery, you are dissipating that heat via resistor. In active cell balancing, you don't dissipate it. You transfer the energy to the subsequent cell, the nearby cells. Okay, this is how the cell balancing for active to passive is different, and it is very important function of BMS battery management system to perform this so that my all the cells are equally charged. They all achieve the same voltage while charging. For suppose if my threshold is 4.2 voltage, so all of my cells like 16 series cells, all of them should be in the same voltage level, right? This is something very important so that you can get the best or maximum juice out of the battery pack. Okay. There are some protection algorithms also, right? There's something on overcurrent protection. Let me see if Amit also joined. If he's not joined, I'll continue this. Yeah, Amit has joined back. Amit, are you there? Or shall I?
Yeah, Vishal.
Yes.
Sorry, I'm
Okay,
there.
okay.
Actually, my internet
No worries,
just
no
dropped
worries. I think you are the
in
right
between.
person
I
to
don't know
continue
why.
from here. Yeah, no worries. I'll stop sharing, Amit. You can start sharing
Okay.
again. And sorry, folks, all of the folks,
Okay.
we
Okay.
got
No problem.
this in between. You can start sharing, Amit.
Yeah. Okay. Yeah. Just give me 1 second. . Okay, so yeah, sorry for my internet connection. It just dropped in between. So, okay, so we are back. So, okay, we were discussing regarding cell balancing. Okay, so why this particular cell balancing is required? And first of all, let us see what it is. Over here, you can see that there are 4 cells connected in series. Okay, so cell number 1, cell 2, cell 3, cell 4. And what happens during this charging, or during, also of course during discharging? So there are multiple concepts. Some of the BMS does cell balancing during charging, and some used to do cell balancing during discharging. But the common practice is we do cell balancing during charging, because it helps us in many other aspects that we will look into detail in our battery course. Okay, let me turn on my pointer. Okay, so imagine that we have 4 cells in our battery pack, and during charging, what happens that every cell will not charge at the same rate. Some will charge fast and some will charge a bit slower. And why that happens? That happens because some of the cells will age because of the aging factor. Some of the cells age much quickly. Some of the cells ages less quicker than other cells in the battery pack. And what is the prime factor that changes during aging is the internal cell resistance. There is something, a concept called DCR of a cell. That is my internal parasitic resistance of the cell. So imagine if cell number 1 is weak, this will charge much quicker than other 3 cells. So what happens during charging? Imagine the charge current is flowing from cell number 1 to cell 4. Cell number 1 will hit the top cutoff voltage, that I would say it will be around 4.2, 4.25 volts, as we have seen in the previous slides. So it will hit my top cutoff voltage much before my cell number 2, 3, or 4 has reached. So during that time, what BMS will think that cell number 1 has already reached the top cutoff voltage, and you will cut off the charge. And if we do like this, then that means the cell number 2, cell number 3, cell number 4, these 3 cells have not reached its full cutoff voltage, and cell number 1 has reached. That means cell number 2, 3, 4 is not fully charged. Only cell number 1 is fully charged. And during that condition, the whole entire battery pack will perform less. Why? Because 3 cells are not fully charged, only 1 cell is fully charged. So to not have this type of situation inside our battery pack, we introduce a function that is called cell balancing. And what it does, it equally distributes the charge over all of my individual cells. And how BMS does the cell balancing? Imagine this particular cell number 1 has reached its full cutoff voltage. It will allow this cell number 1 to discharge through its, so there will be a MOSFET that is placed inside the controller of my battery pack. And this MOSFET will turn on. And this MOSFET, what it does, there will be a path. This resistance is selected. And through this resistance, this MOSFET will start discharging my cell number 1. So my cell number 1 will start discharging up to a particular point. BMS will discharge the cell number 1. Again, it will stop discharging the cell and the charging will continue. So, and because of this, my cell number 2, cell number 3, cell number 4 will reach to its full potential. And the final battery pack will be in that state in which all the cells have the same amount of charge stored inside. And my battery pack can perform with its full potential. So that is what is cell balancing. So you discharge a particular cell and then again start charging the cell so that my another cells which are less charged gets to its full potential and without damaging cell number 1. So because as we have seen that we cannot overcharge the cell. So when a particular cell reaches its full voltage, we have to stop the charge, slightly discharge this with the cell which has already reached the full voltage, and then again start charging. So that because of which my other cells which are less charged compared to cell number 1 will also get fully charged. So this is called cell balancing. We will look into the hardware design of this cell balancing in our coming battery courses. Okay, so let's go to our next slide. Another function that BMS does is that is called overcurrent protection. So why overcurrent protection is required in the BMS is we know that cells have a property, we cannot discharge a cell beyond a certain current limit. That means if my cells are rated for discharge current, let's say 2C, and my cell capacity is 200 Ah. So that means we cannot discharge the cell 2 times the capacity of the cell. That means capacity is 200 Ah. That means we cannot discharge more than 400 amps of current. And for the BMS, and there are certain conditions in which it happens, like short circuit and like that type of situation, in which my current can go more than the rated capacity of my cells. So during those conditions, BMS has to protect the battery pack, and it has and one of the protection mechanism which are inbuilt in BMS is called self-controlled protector. So this is nothing but this is like a fuse, and it has 3 terminals. You can see over here there are T1 terminal, T3 and T2, and there is a inbuilt heater in this particular type of a fuse. So what BMS does, when it senses that my current is crossing over a certain limit which should not cross, it activates this heater. And what this heater do, it blows off these fuse and cuts off the current flowing out from the battery pack. Or it actually works in both the side. It also works during charge and during discharge. So during charge, if there is some type of a short circuit which is consuming more current from the battery pack, it cuts off during that time. And during charge, when there is excessive current that is flowing inside my battery pack, it also operates during that time. Okay, let's go a little bit more. Okay, and it also, this particular type of a switch is also necessary for over voltage protection. So this SCP, that means self-controlled protector, is used in both the condition. Because it is, and first of all, why it is called a SCP? Because BMS or a secondary protection IC can operate this resistor element by using a MOSFET. So this fuse is a controlled fuse. This is not like an uncontrolled fuse based on just only current. This fuse can be operated externally. So there will be a IC that senses my voltage cell. This particular over here, you can see that there is a secondary protection IC which is measuring my battery pack voltage. So during charging, if my cell or my battery pack voltage cross a specific limit, this secondary protection IC will operate this MOSFET. This MOSFET will turn on this heater and it will blow off my path or the main current path. And because of this, my battery pack will get protected. It will not overcharge or and it operates in both the condition. Over here, I have shown just the over voltage condition, but it operates during excessive current also. Okay. And another protection circuit over here I have shown, this is nothing but a general fuse. So we also use something called a general fuse. So this is just one specific form of a fuse I have shown over here. This is something that this is called tubular fuse. This comes as a cylinder and the fuse element is inside this. And I hope like most of us already have experience of using a fuse in a circuit. And why fuse is required? It protects from overcurrent. Okay. So let us look into the blow off time. So, and how this particular type of fuse is selected is also purely dependent upon our battery pack application. Like we are using battery pack for a low current application, high current application, selection of this fuse is completely dependent upon my battery pack application. So one example over here, like imagine this is a 100 amps rated fuse, and this is the graph of the fuse. Okay, so how we will choose, like imagine if this battery pack is rated for only 100 amps. So definitely we will use a 200 amp fuse during that time. But if this, imagine this battery pack is rated for 70 amps, we will use a 100 amp fuse. And how we will choose fuse? Based on its time and current graph. So let us look how this time and current graph looks like. This is the time and current graph for this 100 amp fuse. You can see this particular fuse, if it is rated for 100 amps, so this is my 100 amps, it can work indefinitely. And if my current goes to 200 amps, you can see it will blow almost within 1 to 2 seconds. And if it goes to 300 amps, it will blow. This is 0.1, 0.2, and 0.3. So it will blow somewhere between 0.25 seconds. 0.25 seconds. So based on this time and current graph of this fuse, we used to do selection of this fuse that will match our battery pack application. This we will look into detail when we go much in. We will go into detail of in our battery pack course. Okay, so this is what is overview of our hardwares that are used in our battery management system design. And in our course, we will look into more into details about algorithms, that of course we have gone through some of the protection and protection circuits. What type of communication protocols are used? Like imagine like some of the battery packs generally in automotive, we know that we use CAN and LIN. So these two are the common protocols that are used in automotive. So we will go through that also. And there is something called regeneration. So how BMS used to control regeneration and the switching circuits. That means turning on and turning off the HV. And we will look into selection of components. Selection of components are very important during any hardware design. How we select our component we will go through the data sheet. We will see what is the requirement that we have for our battery pack, and we will correlate that the components that we are selecting matches our requirement, or I would say application of our battery pack. So first we have to decide our application, then from application comes out the requirement, and based on the requirement we select the components. Then how we do the microcontroller selection. This is of course the prime important part inside the BMS. Why? Because microcontroller does all the functions and it is nothing but the mind of the BMS. So this particular part is very important. And how the hardware is constructed. Hardware construction in a sense like how we design schematic to PCB to Gerber generation, then we get the board, and how we do the component placing, and then what are the steps that we do for board bring up activity, and then how we fix our, that means how we attach our BMS to the main battery pack and test our main battery pack. And then some of the things like over here, today we have seen a small example of our pre-charge simulation. So like that, there are many other simulations that we will do in our main course, like HV turn on, HV turn off. We will do for cell balancing. We will do for, of course, pre-charge is, I have just shown a small example, but during our main course, we will show how the components are selected for a specific pre-charge application. So, and definitely many more. Okay, so I hope most of the things are covered at the moment. I can transfer over to Vishal to carry forward.
Yeah, thank you, Amit. I think we need to stop sharing so that I can share my screen, and
Okay,
I'll
yeah.
brief about Techlanz also. Can you stop sharing, Amit, please?
Yeah, just give me 1 minute. Yeah.
Yes. Okay, I hope it was very engaging session for all of you. And so we just brief about what Techlanz is. So Techlanz, okay, sometime it happens. Yeah. So who we are at the first place, right? So Techlanz is a ecosystem of electric vehicle development. We provide training programs across by the industry experts across. So each of every program consists of 5 to 6 industry experts, so that each of every module is taken by expert industry expert. We also provide you real hardware in the training program so that you can learn on the real hardware by practicing at your home. We also a provider of engineering services. We provide, if you go to the website, I'll share the link just right away after this. So we provide multiple kind of engineering services from simulation, system engineering, and all those things. We also conduct these kind of webinars because we strongly believe the growth of engineering community happens by these webinars. We have our industry partners also. They help us in conducting these kind of webinars so that the information, the base level information is shared across multiple people and engineering community can learn and grow more. We're also building a very big engineering community where you can exchange your ideas, discuss your problems. Like many questions were raised in the chat, right? So, what if you have a community, an open source community, like Stack Overflow, you might have heard, right? And where you can openly ask your questions, and there are industry experts from across the globe which are there to help you to answer those questions. You are building those kind of community. How we are building that? So we have two communities with us. One is WhatsApp community, and we are also building an online community, like a complete platform which is already there on our website, like Stack Overflow. I'm just giving example because for IT industry, Stack Overflow is very important. They used to ask everything from Stack Overflow, but for a hardcore engineering thing, that kind of thing is missing. Meanwhile, Amit, there are multiple questions in the chat.
Yeah,
Uh,
yeah, I'm
type the answer to few of them, right? Based on your convenience.
yeah.
We also, yeah, thank you. We also have our website. You can go through it. We also offer multiple courses. Now, in the next slide, I'm going to tell you about our courses, Battery Plus BMS Bootcamp. uh, what we are offering in that. Interested people can stay. Other people who are not interested in the course, I don't want to spam people. This is something very important. We want to make sure that we are delivering the right value to people and the learners, right? And we'll cover what you are covering in that course. So our Battery Plus BMS Bootcamp is divided in 5 sections. So we believe that it's very important to go through each and every section so that you can become a complete battery pack engineer. In the first module, we'll be taking you through the cell fundamentals, cell testing, cell modeling. So everything regarding the lithium ion cell will cover in that. Then we are dwelling in the BMS hardware design. We'll talk about what is PCB design, component selection, circuit simulation, schematic design, what Amit already explained you, right? We'll go much more deep in that complete module, which will be lasting more than a month, where you learn the complete BMS hardware design. We will also go and cover the complete BMS algorithm. If you have watched our previous webinar, we covered some of the aspect of RC modeling and SOC algorithms. We will take you through that complete algorithm development of the BMS. Then we'll stitch all these things together with a BMS firmware design, where we'll be covering the BMS firmware design process. We will see the microcontroller data sheet and understand how to write the software or firmware on that microcontroller. We'll also do the communication protocols, UART, I2C, SPI protocols. We'll take you through that, how to display something, how to connect everything, and how to communicate within the BMS hardware itself. At the end, we'll stitch together the algorithm developed from here and the hardware design to make a complete BMS firmware for a complete battery management system. When you have all these pieces of puzzle together, we'll join them together in a battery pack design where you'll understand how the things are connected, how the complete battery pack construction is done, how the mechanical design is done, how the electrical design is done, and what are different regulatory consideration or homologation consideration while making this battery pack. So at the end, we want to connect all these things together, right, and make the complete battery pack. Now, there will be multiple projects as a part of this, right? Like cell modeling, RC modeling, physics-based modeling, data-driven modeling that will be part of this first module. We'll be doing the complete BMS PCB design, assembly, component selection will be part of these projects. multiple SOX algorithm, SOC, SOH will be covered as a part of algorithms. Complete firmware design and embedded C will be covered. The circuit simulations will be covered, and many more things are covered as a part of the project. So that will be a really hands-on learning for you. Apart from that, we also cover multiple tools, which is very important because industry needs are based on tools. If you don't know the tools, it's very difficult to get you the right skill set. So we are taking you through all the MATLAB, Simulink, Stateflow for all the algorithm designs and all. For the embedded software, we are taking you through the STM32 IDE and Keel Microvision. We'll also do circuit simulation using TINA Spice, LT Spice, the PCB design using Autodesk Eagle. We'll do the data-driven modeling and some other algorithms using Python. For the physics-based modeling, we'll take through the console. So these are the projects and software, the tools which will be using it, as well as we are giving you this hardware kit, which is single cell BMS, so that you can practice at your home. When we give you all these things, the objective of giving a single cell BMS, because in the class we are teaching you how to build a 48 volt or 60 volt BMS for a small application, but that becomes very risky to offer you because it's a high voltage system, and if something goes wrong, it's very risky. So to deliver that lecture safely and to take you through all the algorithms and everything, we have custom developed this hardware which will be dispatched to your home. So all the algorithms which you learn, all the firmware development, SOC algorithm or MBD algorithm, you can flash on this hardware and you can practice those things, which is a similar to actual BMS, but this is much more safer and much more convenient for you to learn that, right? And we have a display LCD, you can see all those things when the things are displayed in front of you.